biologists about the role of this DBE. Okay, and this is the very first model. And in this model, they propose that actually phytoglycogen is an intermediate of amylopectin. Okay, so if you see some figure C, this is what they believe to be phytoglycogen, or they call it p-amylopectin. Okay, and so you see that by getting SS and DB work together alone, then we will get these random branch points, like you see in phytoglycogen molecules, right? But then if you have intact DBE in the cells, then DBE will selectively cut those excess branches, and then the molecule becomes the final natural product of amylopectin. Another paper gives more detail about the underlying mechanism. So this is just an idea, rough idea for biologists. Okay? So rigorous proof. So what they propose is that from other experiments, it was shown that two adjacent chains can form a double helix structure, like you see here. And this feature, I didn't have this feature in my model yet. Okay? So they hypothesized that two adjacent chains can form the double helix structure. But if you have excess branch points, then these excess branches will prohibit the formation of the double helix. Okay? So in normal cell, DBE will cut these excess branch points and let the adjacent chains to form double helix structure, and that will become normal amylopectin molecules. Okay? But without DBE, then this region of the molecule cannot form double helix structure, and it will become phytoglycogen. So this is what we propose from experiments. So, but I have to say, sorry that I don't have a final result yet. So the next step is to implement the idea of DBE from different conceptual models from literature that I have, and integrate them with my model that I have, and see what would happen. So but now I will move into different direction. Okay, so far I talked about qualitative properties of the molecules, right? Talking about the arithmetic pattern of the molecule. But another nice thing about doing simulation modeling is that you can do quantitative analysis aspect. Okay, so from experiments, we can say we have this amylopectin molecule, right? We can use an enzyme to digest all branch points, but keeping the length of each chain unperturbed. Then you can separate each chain by its length, right? And then plot it on this graph. You will get the distribution of the length of each chain in the molecule. Okay? So the x-axis is the number of glucose units in each chain. Okay, so in this one, so here this is the chain that has 10 glucose units. Okay, and the y-axis is just the ratio of the number of glucose units in particular chains divided by the total number of glucose units. Okay, so this part just tells you the distribution of the length of the chains of the chains in the amylopectin molecule. And if you look at the blue bars here, you see that for normal amylopectin molecules, the peak of the chain length is about 10 or 12 glucose units. Okay? So this is the quantitative property that we can use to compare, to validate our simulation. Okay? And because I haven't got this right structure yet, okay, so I just try to see what if I just use what I have here and then do exactly the same thing as the experiment. So I just calculate the length of the chains in this molecule, plot it exactly like what we see here. Okay? And so what I get is that I get the peak of the length at about 12 to 13 or 14. Okay? And if you wonder why my plot is not as smooth as the experiments, that because for this model I have only 900 chains. Okay? So, but I just want to show you that, so if we do the simulation, we can compare our model to experiments. Okay? So I have to tell you that this project is in its initial stage. Okay? So it is not finished yet. And what I'm going to do next is that I will try to propose a minimal mechanistic model that incorporates different enzymes involved in this process. Okay? And try to explain how the structure of the arithmetic pattern of the amylopectin molecule occurs. Okay? And I will also try to fit my model to experiment observations. Okay? So let me just summarize on what I have done. So I guess the main points of doing simulation and modeling is that you can, once you get the model, you can do the simulation and see the consequences of the model, right? And that is the and you can use modeling as the visualizing tool, okay? And you can also do quantitative analysis. And more importantly, you can use modeling to do hypothesis testing, right? If you have different assumptions, different models proposed by, say, biologists from evidence from experiments, you can use simulation to test which one is the correct one. Maybe model A or B, or maybe the combination of two models, right? That is the power of simulation and modeling. Okay? So this project is part of the bigger project led by Ajahn Vinod and Ajahn Sawayak, whose research is about the study of classical starch metabolism. Okay? And this project is funded by the Vijay Majatao and has Ajahn Barasi as a mentor. Okay? So thank you everyone for your attention. And if you have any questions, please feel free to ask. Okay, so basically when we simulate something, we want to like say if you want to say that your model is at least not wrong, okay, maybe it's not right, at least not wrong, you have to find some supporting evidence, right? And one way is to use quantitative analysis, use something that you can measure, that you can compare to experimental observations. Did I answer your question?
Other than quantitative analysis, do you have any other means to calculate?
Actually, for the
We don't hear the question. Could you please repeat the question, please?
And I will repeat the question in the
okay.
microphone so that
So Theomo is asking that other than quantitative comparison, right? Do I have any other ways to validate the model? Right? Okay, so I guess for the quantitative part of the model that we want to get those mathematical patterns of the molecule, right? I'm thinking about, I'm not sure if this is the best way to validate the model, but I'm thinking about using a clustering algorithm somehow that you can use some statistics to cluster the bunch points of the molecules. Okay, so if the pattern is clearly clustered into groups, then some statistical tools would be able to distinguish this group from this group, right? And if you apply the same thing for this molecule, then that would tell you that they cannot cluster anything from the structure. This is just an idea that I'm thinking about, but I'm not sure how to approach it yet. Is two-dimensional for now.
In reality, it's probably giving you different results in 3 dimensions.
Yes, actually, it is debatable between two groups of experimentalists. One group says that the growth of this molecule happens in 2D, but another group tries to propose that it is actually 3D structure.
Another question is, what about the interactions of the molecules with your bounding box? The bounding box doesn't exist in nature, but in your simulation you deal with finite size, 900 or 1,000 chains. So what happens when these chains reach the boundary of your...
In my program, it just stopped. But I can just increase the size of the box.
Because when that happens, it may actually also influence the results. You stop at the box,
Yes.
so you get repeating periods that depends on the box size.
Yeah. So in my program, I just terminate the simulation if it reaches one size of the box.
Just an interesting idea, maybe, I'm not sure. But what determines the structure of macromolecules, polymers, is basically minimizing the free volume. So it might be a good idea to have a cost function that includes free volume. And a branching plane would not allow an as dense packing of the glucose as you would have in the linear chain part. This may help you. Maybe this is